Annyeong, Hashemniga. Hello everyone, big thanks for joining us here. I have to say, after a very exciting week, so this is my last event before I have to fly back to Europe. And you see already I started here with a big pack of business cards. This is my last 5 that I'm surviving with at the moment. So it was really engaging week, not only yesterday at the Innovation Days, but in various customer meetings this weekend, and really a good exchange, a good discussion that we had, especially of course with our favorite customers in the Korean market. Before I start discussing with you about our portfolio and especially about the Ethernet technology, what I would like to do is I would like to show you a little video that we have made last year with a company that is called Rinspeed. Rinspeed is since 40 years doing concept cars for the Geneva Auto Salon, which is a bit the crazy side of car making, car tuning. And in 2007, this company Rinspeed also did this swimming and diving James Bond car, this Lotus car that you might know from these James Bond movies. Yeah? So always a bit with a smile in the face, they try to translate what's going to come in future in automotive. And they have asked us last year to be their partner as a thought leader and to pitch with them the brave new world in automotive. And I'm going to show you very quickly how that video from an NXP perspective is. So a very short, very wild pitch, of course, into the brave new world of automotive. And a lot of these technologies you will see now in the presentation coming back, of course, with more technical background. The video is, by the way, is also on YouTube, where you easily can have a second look and so on, because a lot of the stories that are buried in that video you will not discover at the first step. So, if I may quickly introduce you into NXP, and especially, of course, NXP Automotive. NXP is the former Philips Semiconductors. We spun out of Philips in 2006 and have since then had a very big turnaround in the company. So we were private equity owned, a lot of business parts have been divested, and we focused in principle on being a true interface company. So true interface company means NXP is providing all sorts of electrical interfaces, wired and wireless interfaces. And what you can see here already, it's difficult to read, but of course what we expect is 50 billion devices by 2020 to be connected to the Internet of Things. For sure that figure is wrong. It will be 30 or 80 billion. It will be huge. Yeah? We don't know yet what it will be. But what is clear is one thing. To have a device that is connected to the Internet of Things means that this device needs electrical interfaces. So that is a reason why the analysts looked at our portfolio and immediately spotted that this portfolio basically is the core portfolio for the Internet of Things for connected devices. And also what NXP is market leader for smart card security. So if you assume that you have an exponential growth for connected devices, if you furthermore assume that these devices need security and NXP has the security chips, of course, the hope of the market is that NXP will big time benefit in that upswing of connected devices in the Internet of Things. And this is, by the way, by our share price since the IPO. started at $12 and is now in the range of $100 at the moment. Yeah, and I hope, of course, for me personally, that this is not the limit, so that we will be much more successful over the next coming years. But what you can see is NXP has turned around since 2008, really since the economic crisis, into a very, very successful semiconductor company. And in March we have announced that we're gonna marry Freescale semiconductors, and I'm gonna show you in a few slides how that is gonna move forward now, what that means to the market, how we're gonna go into the market as we see it in the coming years. So as said, NXP is of course active in automotive. With the merge of Freescale, we will be the biggest automotive chip supplier in the world. But we are of course also supplying our technologies, our interfaces into all other sorts of markets, and of course with a strong portfolio in security. You can see us active in 700 transport cards of the biggest cities worldwide. We are in health cards, we are strong in banking cards. We are in these RFID tags, long-range RFID tags, even in license plates with our RFID tags. We are in avionics, and of course we are also in home automation. Because what we have is, we have car keys. We are market leader for car keys. But communicating to a car and telling the car, please open up or please close, is the same functionality that you can use for telling a Wi-Fi router about the smart meter information in your house. A little crypto channel, low data rates, but very energy saving, operating on a coin cell. And these technologies, of course, we are exporting from one market into the other. The semiconductor business, we want to have economies of scale, of course. That's the old name of the game. If I now look into the automotive market, what is fueling the automotive market is basically three big trends. Well, the one trend, of course, is we want to have cars that consume carbon dioxide and don't produce carbon dioxide. Yeah. So ideally, electric drivetrain, zero emission, if possible. NXP is not the market leader for steering these big electric engines, but we are leading in getting the right information into the hybrid vehicle, telling the hybrid vehicle then to switch from the combustion engine to the electric engine and the other way around. So the smartness, the information routing in the car, that's our home domain. Then what you have here on the left side is, of course, the old inheritage of Philips semiconductors. Philips transistor radios, everyone knew. Connectivity, AM, FM radio chipsets, of course, is a home turf of NXP. We have a very strong IP portfolio in that domain. And this is, of course, a growing trend. In your car, you want to be connected like in your living room. Yeah? Sitting on the sofa or sitting in the car, you want to listen to every kind of content, music, hear books, whatsoever. You want to talk to any person globally. And the hottest trend is, of course, the blue one in the middle. How do we convert now a car from a, let's say, better horse carriage into a self-driving robot? How does the car take over the driving task from us? And this is basically what you can see on the next slide. How does a robot work? An industry robot or a car or a flying machine whatsoever. Well, you have a sensing part to recognize your environment. Then, with that information, you do what we call in techie terms sensor fusion. So you do basically a driving advice for your car out of all context information. You try to calculate how the car should drive. And then you communicate that information to your actuators, to your arms and legs of the car. You accelerate, decelerate, or you steer. Or switch on the light, or your amplifiers. So your input-output areas. Input, think, output. These white boxes here with the orange frame are the boxes where NXP is market leader or has a very, very strong business development pitch. So where we have breakthrough technology. Every third ABS sensor is coming from NXP already today, worldwide, if you would rate this over the entire car. We are very strong in business developing in new radar, new car-to-car communication. We have smart car access, we are number one in car keys. And we have radio domain, leading portfolio. Solid state lighting, amplifiers. And that whole thing needs to go together via these little lines here. And this is what I'm going to talk about today. This is what we call IDN, or in vehicle network. So this is physical layers. This is the in-car interfaces between the control units. That was a slide that I've made mid of last year to explain to analysts what NXP is doing. NXP is not active in these gray areas. In these gray areas, companies like Freescale are market leading. And now you got the story, what we have announced in March. Just assuming that these gray boxes turn into white boxes with an orange frame, we can deliver almost the entire portfolio for all these systems to become market leader and provide really not only the sensing part, but also the thinking part, in certain areas even the actuating part. And that is of course a great offering to the market, saying you get a pre-qualified reference design from our side, you get much easier access to technology without spending huge amounts of R&D, but you can very easily take what we have already in our laboratories and make it automotive fit for your car brands, for your portfolio, for the sizes that you need. High-end, mid-end, low-end cars. Very easy.
So the last point is your technology portfolio and scale technology portfolio must be some sort of compatible and interoperable with each other. Because Scale is working together another sort of sensor company, interface company, to provide total solution. We're working with another MCU company to provide total solution. So how to harmonize the
well, as always in the market, of course, we are not exclusively tied to each other, but we have flexible portfolios, and already as of today. So what you see here is basically a demonstrator that is already partially running with I.MX microprocessors, and in the radio domain we have demo radios where we have our radio solutions and where we have Freescale microprocessors already in. This was nothing that we did new after the announcement of the merge, but that was something that we basically did already in the last 1-2 years. So our car-to-car solutions are microcontroller equipped, so our own demos with Freescale microcontrollers as of today, and we have been partnering all over the past. Not exclusively, because that would be stupid, if we would go into niches and say, only the two of us can work together. But there was already a strong partnering, and I think the rationale for that entire deal is why we are so excited about it. Is of course that it is simply such a good fit. Usually you have M&A deals where someone goes in and just takes out cost and chops of pieces of a company to get cost savings. In this case here, this is absolutely not the case. We have a great potential to just glue the two businesses together and grow into much better offerings for our customers. Yeah, perfect from that angle, and very energizing, of course. So looking back into today's NXP portfolio, what do we have? We are number one in infotainment chips, car radio chips. 19 of the top 20 car radio makers are using our car radio chips. Of course, as I said, we started from a Philips in heritage AM/FM transistor radios, class AB amplifiers, so that's basically the base level. And then we moved to very energy efficient class D amplifiers and RF CMOS 1 chips. What that means is we have the tuner and the baseband in CMOS for the first time combined. A lot of our competitors had the tuners in one technology and the baseband in another technology, so you never could merge that into a one chip. Basically what you have now as of today is basically you can take these chips and you can make them, even for digital radio reception, software programmable. So the software programmability is of course one thing where you have a Korean digital radio standard, a German one and a Canadian one. Just think of HKMC, they would have to develop 3 different radios, have to qualify 3 different radios, and all for a pretty small market, for the German market, for the Korean market, and for the Canadian market. What a nightmare, yeah? Instead of that, they can take one of our chips, say, okay, the hardware is always the same, and I'm changing the software on top of that. I'm just changing the software to the Korean standard, to the German standard, and even while I'm driving, I can change. Yeah? So who cares whether France has a different standard than Germany? When I cross the border, I just know via GPS where I am, I swap. Yeah? So very easy. And that is of course, one chip receives everything, is the road to go here. The other thing is the car keys, as I mentioned prior. We started 20 years ago with immobilizers for cars. And these immobilizers are nothing else than little crypto chips. We moved that into remote keys. From these remote keys, we moved into so-called two-way keys. This is car keys that range over 1 kilometer of distance, 1,000 meters in the open field. So I can sit here and say, okay, the session is over. I press my key and the climate control goes on in my car. I switch my laptop down, go down, 10 minutes later, my car is climatized already, I can drive. The same silicon is that silicon that we use also for the smart meter to Wi-Fi plug at home. And what we have is, we have passive keyless entry and passive keyless go, as we call it. A chip of the size of my little fingernail that can easily fit into a smartwatch or into a smartphone already, but is in principle a complete key. So I have this key in my pocket. I do not need to operate that key anymore, so press open or close. No, I approach my car. Out of 10 meters of distance, the car recognizes me and says, hello Lars. So puts the door handles out and puts the welcome light on in my favorite color. So whether it's pink, yellow, green, I have to choose. It's a totally useless use case. But everyone wants to have it. It is hotter than aluminum wheels at cars because you can make your neighbors jealous with it, yeah? So if your car reacts to you like a dog when you come home and your neighbors don't have that. So all the premium car makers are looking into that, and this is one of the fun toys of premium cars in the years to come. The great thing is, of course, that we have this so small, and you can integrate it in all sorts of form factors like variables, smart things. So this is two of our very strong leadership portfolios. The portfolio that we're going to talk about today then is this one here, and you see here already the Ethernet logo appearing. So NXP is also market leader for these IVN physical layers, for these transceivers. For low data rates, very cheap connections between control units, or a switch to a control unit, window lifter for example, you need LIN. Then you have CAN in tons of flavors. So CAN for normal CAN transceivers, of course, CAN for hybrid vehicles, 48 volts approved, CAN for electric vehicles up to 1000 volts for the electric batteries isolated. All that stuff, high data rate, so flexible data rate, partial networking CAN. Then what we have is FlexRay on top of that and Ethernet. So a very, very hot trend in the industry. So basically, how does that in-vehicle networking world look like? The amount of control units in a car is growing like that. So there really you have this interface node count grows as you see it there. Just to give you an example, a Tata Nano has 2 control units in the entire car. So this is basically the engine management and the car access unit, so the key checking unit. That's everything in electronics in the Tata Nano. The Mercedes S-Class has more than 150 of those units per car. In a self-driving car, of course, you have all these different units like radar elements at each corner of the car, up to 10, 15 cameras per car. Just imagine, one modern car, 5 Series BMW, in 3-4 years from now, will have 15 cameras. So traffic sign detection, lane departure warning, blind spot detection, all of these things, interior monitoring, and they are all getting connected. So each one is a separate node, each one is a separate IVN interface. On average, we have more than 10, on average, more than 10 of those interfaces already today in every car that is built worldwide that come from NXP. So if there would be a big bang and NXP would disappear from this planet, you could not even get the cars off the assembly belt at the end of the car mix. What we usually don't use in public is, of course, also airplanes are using these networks and these transceivers very often, and they are heavily relying on these networks. So of course they are much smaller volume and so on, but big airplanes, passenger airplanes, don't even know whether the doors are closed without our CAN transceivers. We have 6 billion of those nodes in the market, of course not all in airplanes. More than 50 different devices, I just said that, that's quite broad. We have 20 years of production, especially in CAN and LIN. And what we are really, really proud of is, but that's of course a figure that has to be very, very carefully watched, we are at the moment far below 1 ppm, parts per million defects in those devices. So this is really what the automotive industry 10 years ago was demanding. We need 0 ppm. We are at the moment at 0.7. This is cool. The only thing is, of course, we need to watch out that not a single incident, not a single manufacturing hiccup or whatsoever can destroy that value proposition. So quality is very, very much on our mind, and also the quality paranoia is there. This is nothing where you can relax on and say, okay, we are there, it's all done. And then, of course, having all of that competence is a great thing, because our customers, the car makers, they are coming to our experts, they're putting a complete wiring harness on the table. And wiring harnesses in luxury cars, they are heavier than iron. They contain more than 6-7 kilometers of cable, and they are the second heaviest device in a car. And they put them on the table and say, can you, NXP, please help us in checking whether our wiring harness, our electronics is robust? So what happens if crazy Lars brings a wireless charge pad and a mobile phone into the car, yeah, and just plugs it into the cigarette lighter? What happens to the airbag system? Is that deploying at 200 kilometers per hour on the motorway? Of course, must not happen. So we are checking the robustness of all of that, yeah? And you can see it here already. What is, of course, the name of the game? The car makers want to have more interfaces in, but want to pay less. So what we do in the electronics is, of course, we try to increase the price of our chips by up-integrating features from around the physical layer. So if you need capacitors, try to up-integrate them. If you need a choke or a coil, try to up-integrate these devices and try to become more. But how does that portfolio look like? Well, you see it here. This is I try to sketch a bit these various flavors. Yeah. So of course we are trying to integrate these network nodes with different functionality, power functionality, all sorts of topics that a new microcontroller would need on an ECU. We call these system basis chips, where we have CAN channels plus LDOs on. And you see here the complete portfolio of that. So 2 CAN, a switch mode power supply, all of that. Then what we have is, of course, we have the flavors of networking features, as I said prior. So we have chokeless CAN. We are saving the coils. So you don't need these coils anymore, expensive coils on the PCBs. We have partial networking. Partial networking is a communication where you can switch off complete CAN networking channels. So just assume you have a car with a trailer hook. How often do you need that trailer hook? Of course, that does not need to be active all the time. Only if you have a trailer, really, that you are pulling with your car. You want that thing to be, of course, active. But in normal use, I would say 99.9% of your driving time, that does not need to consume energy. So there is sleep modes for these whole branches. Then what you need, 48 volts for hybrid cars, the isolated CAN for electric vehicles. And what we have is we have addressable LIN, which is basically a self-learning LIN node for interior lighting, for example. So you have 50 or 70 LEDs inside a car, and it would be a disaster if a car maker would have to have them all in different buckets and say, LED number 1, LED number 2, LED number 3. No, what we do is they are all the same. The manufacturing folks in the plant, they are just putting them onto that cable tree, and then press a button and say, now please learn. You are number 1, you are number 2, you are number 3. And this thing is self-learning with a steering pulse. So the LEDs know where they are in the chain, and they stay programmed. CAN flexible data rate. I said already, this is getting more than 3 megabit over a normal CAN rather than the 500 kilobit. Ethernet we are coming to, and then of course there is different research topics also, and how do we enhance security in these networks? How do we do power line communication? And is there also in automotive a way into wireless communication, so wireless in-vehicle networks? At the moment, the industry is pretty hesitant on those topics here, because they want to see, of course, what happens if you have a disturbing radiation, EMC topics, security attacks from the outside, and so on. But in principle, of course, if the whole world goes wireless, why shouldn't? So basically, what we then have, why are we so strong in that portfolio? Well, very simple. we have great technology, SOI-based technology. So SOI means silicon on insulator, which is basically you do your whole electronics in an insulator layer where you don't have, let's say, a coupling to a substrate in the crystal, in the chip. And that helps us, of course, getting, on the one side, very, very robust against leakage currents. So you can have very high temperatures that you can stand, 200 degrees centigrade and above. Very important if your electronic sits very close to the brakes, for example, that can get ultra hot. So wheel speed sensors or CAN transceivers down there at the brakes are, of course, benefiting from that. The other thing is, if you have an isolation layer, you can have plus minus voltages of, in our case, plus minus 100 volt. So if we do a CAN transceiver, we automatically get this thing isolated for plus minus 48 volts. So our 48 volt CAN portfolio is almost identical with the regular 12 volt CAN portfolio. So it is very, very easy for the car makers. Just take our solutions. They are robust enough for your hybrid cars. Very easy, simple message. And that, of course, that know-how, that IP helps us big time in going into leading edge Ethernet applications for cars and not for computers. Yeah. Then what I said is, we have a huge industrial footprint. I said 800 million transceivers per year we are shipping. This is approximately right, which means that every day we're shipping more than 2 million of those transceivers to the industry. For that, after Fukushima and the Thailand flooding some years ago, and that crazy Iceland volcano 4 years ago, we have, of course, a complete dual sourcing in place. So which you see here, the one is front-end manufacturing in Singapore, the other is in the middle of the Dutch mountains, so in the plain area of the Netherlands, yeah. Which is also so very much liked by the car makers, because a lot of our competitors have, of course, factories that are both very close in same regions. So if you manufacture both in Taiwan and you have an area where you have high earthquake risk or these type of things, we don't have, we are sitting on other sides of the globe. In the future, we are getting a few American fabs also into that game. So we have a very nice Asian, European, American spin of our industrial supply chain. Great, was not planned this way, but perfect if we have it, yeah? And then, of course, what we have is, I said this prior, this is a wiring harness, a picture of a wiring harness. This is what we are testing in Hamburg. So we are using the German military even for these EMC type of pulses and radiation, so where normally the German tanks are tested. So we don't have, of course, tanks on the road, but we want to be at least as robust. And what we have is we have more than 200 people in that domain working. More than 30 people are these system engineers doing this robustness testing and doing the understanding of that magic here in the wiring harness. Yeah, and therefore, of course, we are very high in demand in designing new products, new standards. So what happened in the Ethernet domain also was, some years ago, BMW approached us and said, we know we want to go for Ethernet, but we do not trust the consumer suppliers in Ethernet. We know that you understand these crazy wiring harnesses, and we understand that we know that you understand the automotive quality, that also you are compliant to the processes that we have in place. So if we demand from you that we have an error, we demand from you that you answer within 12 hours with the first reply and within 24 hours with the first analysis. That is, of course, nothing that you get out of the consumer domain. And therefore, they were begging us also and saying it would be fantastic if you just could do an Ethernet development. And what we of course had is, why at all the request for Ethernet? Well, you have seen it on that prior diagram. There is CAN, LIN, and FlexRay. LIN is doing 20 kilobits per second. CAN normally is doing 500 kilobits per second. FlexRay is doing 10 megabits per second. That does not sound, from a consumer perspective, overly exciting in terms of bandwidth. Well, the automotive industry had already MOST, M-O-S-T, as a network, but still the issue that, hey, it is proprietary automotive. We are only building 80 million cars. If this is the entire industry that tries to bring a standard forward that is either super slow, super subscale, so economies of scale are not given, and we have to develop everything ourselves, and that takes us 10 years. So FlexRay was one example that is took endless, and everyone was afraid, of course, of that. And now we are seeing that cars get more and more industrial robots. You need higher bandwidth, and you need very fast reply times. Otherwise, no driving robot. Of course, the consumers also want to have seamless infotainment in the cars. So better backbones there. Had already PCs with IP interfaces. There is IP cameras out there for robots. Yeah, if there is industrial grade cameras, why should I develop automotive cameras and all of that? So in principle, that machine wants to go to sleep all the time. This is of course everything that they need, and the other systems will benefit from that higher bandwidth. So very simple message: let us steal from other industries. Let us steal from the telecommunications industry and computer industry first. Aerospace was there already, also big cruise ships, but of course they are super small volume, and industrial robots and automation. So the idea was, of course, if you could take the Ethernet IEEE standardization, it would be faster. We have a bigger economy of scale also for the software development, for the MAC layers on the microcontrollers and so on. We can steal all of that. And the world has already IP and engineering know-how in that domain. So it was pretty logical. The only thing is, and that is really a pain in the neck, is consumer computer Ethernet for 100 megabit has 4 wires instead of 2 for CAN. So this big fat wiring harness gets heavier the more Ethernet I put on. And then of course the guys came back and said, hey, NXP, can you help us drive down the bill of material? Do you have any idea for single, unshielded, twisted pair? So the phone wires. The crappiest, cheapest cable that we can get in the market, and you still want to have 100 megabit and automotive robustness. I said, gee, okay, good wish list, very nice. Of course, the idea was the weight reduction of the Ethernet thing, and of course, getting simpler just by having the right connectors, so taking the CAN connectors that you anyhow had in the automotive market, taking the cabling, the wiring that you already had from the CAN buses in the system. We founded together with BMW and some other car makers the Open Alliance. This is this logo of the Open Alliance, and here you see this unshielded twisted pair cable already. That is the idea, of course. That Open Alliance had over, I think, 9 months, 180 participants, all tier 1s, all car makers worldwide, and most of the tier 2s. But we were totally run over by the amount of success that we had there. And I was leading in 2010 that division, that IDN division that was working on Ethernet. And yeah, so we kicked that off. That was really in 2009 where we completely were overrun by that demand. 2 things we did not know in 2010, how we get them under control. So this EMC topic, reducing all of the requirements, getting higher data rates over the cables, but then being even better in EMC. The quality, temperature range, and also the power consumption was quite a challenge. Nevertheless, that market looks attractive. So this is, what is it? It's Gartner forecasts, so market research forecasts on how many ports do you see by which year. So as always in automotive here, nothing happens overnight. So that is almost 1 decade in terms of market intro. We are here at the moment. Ethernet, there is a few million Ethernet nodes already in the ports in the market already. It's forecasted to be pretty high in 2023. A small chunk of that is gigabit Ethernet. That is also by this Open Alliance driven into 2-wire unshielded twisted pair gigabit. That is the research that's going on at the moment, the development. Some 100 megabit 4-wire lines still existing in the market today. And then the broader reach, Open Alliance broader reach is this standard here. This is the standard that we have developed. Have we developed that? No, we have not. We licensed the patents from Broadcom, because what had Broadcom done prior? Broadcom had done voice over IP systems. So they were taking out analog telephones out of houses, then they had a phone wire in the house, and were plugging in Ethernet from two sides and said, now we can do voice over IP. So computer to computer where prior telephones had been. This is called broader reach. We licensed their patents so that we cannot be sued by Broadcom, but we did our own implementation of this broader reach standard, and that was the great thing. And this is how it looks like. What we have available now for our customers is these physical layer chips. Plus what we have available is an Ethernet switch. So this is basically a 5-port switch. And we have partnered, so here we have licensed Broadcom standards. Here, from the company TTTech, we have licensed IP also for deterministic Ethernet. And that is what that is, I'll tell you in a few slides. But in principle, what you can do is with those two chips, you have two Lego blocks. Why did we do that partitioning and not up-integrate all in one chip at the moment? Because at the moment we have no clue how the network topology of the various car makers is going to look like. Yeah? Some of the car makers say, we have one Ethernet branch with let's say 6, 7, 8 of those nodes, and each of those nodes is going as a one-point connection to a radar system. Then the others say, no, that doesn't make sense. Yeah, we have only two at one switch, and we are done. So basically, what we had long considerations in how do we do the partitioning to have the best entry into the market in such an emerging market. So what we do is we have single port physical layers. We have, of course, these two glued in one chip, dual port, but then we have a 5-port switch, and this is basically connected either to a host controller, so if you only have that lower part of the story, or of course you can extend to have them more and concatenate these devices to each other. Yeah? The cool thing is here, these physical layers have also the low power management, low power capabilities. We have stolen that from our partial networking CAN transceivers, and what that means is the following. Whenever there is no traffic on the Ethernet bus that is relevant for this control unit, then this whole thing goes to sleep. If you would do this with existing Broadcom broader reach solutions, you cannot reach that low power levels, and the idea is, of course, to go to microwatts in power consumption as long as the system is not needed. Automatically that thing goes down. Microcontroller, Mac layer, everything to sleep. If there is a wake-up call, then this device here is listening, but only with the watchdog, so only the watchdog is alive. Yeah, the watchdog has the ear at the rail and says, any data package coming, anything coming, okay. If something is coming, wake up the whole enchilada here. Hey, everyone, up to work, let's go. Here, basically, they are all in standby. Worst case, the entire system is waiting for the package to come in and is consuming in the range of 1 watt. So this is here a factor of 10,000 at least that you have in power consumption reduction. Yeah? And that's of course massive. Yeah. With some of the sleep modes, low power standards that we see in the industry, you can go down to 2 milliwatts. But here is another order of magnitude, at least in between. This is what we of course want to achieve. This is our value proposition into the market, to go out to the car makers and say, you want to have green cars, take our silicon, you're there. Yeah? And that's the type of know-how that we brought into the, in principle, existing ideas of broader reach 2-via Ethernet. For that switch, you have always this discussion on, there is certain applications that need some sort of data streaming, that need some sort of data supply, but that's not time critical. Other things, like there's FlexRay at the moment needed, are highly time critical for all these X-by-wire applications. So if you do brake-by-wire, steer-by-wire, fly-by-wire, the last thing that you need is that your machine says, I heard your signal, but now I'm doing a 1-second wait state, I brake in 1 second. This is of course not what you can use for driving robots. So there is a mix of synchronous traffic. If an action comes, that system has to react. And there is standard Ethernet traffic where you say, just make sure that enough data is constantly running into my buffer of a multimedia streaming, and then I work out of that buffer, that's all fine. So there is very different classes of Ethernet traffic on the network. If everything would be highly synchronous, you would have an enormous overhead to manage and your data rate would go down. Doesn't make sense. If everything would be super sloppy, yeah, then your system is totally unpredictable because it depends on the system load, on the bus load, what really is reaching which application. Yeah? And from that, you have the various standards with low criticality, the normal 802.11.3 IEEE standard, streaming standards where you don't want to have interruptions while you're doing video streaming, of course. For an email, it's totally uncritical whether that's coming in, when that's coming in, or if it's coming in jobs. Then you have real-time controls, and then you have things that must not go wrong. So break-by-wire must not go wrong. Also on an Airbus A380, fly-by-wire must not go wrong. Otherwise, I have an issue coming home tomorrow. So that's basically what we have. We have licensed this IP from the company TTTech that had normal Ethernet switches already in the market for time-triggered Ethernet, so time-triggered technologies is TTTech, yeah, and they are a daughter company partially owned by Audi. And we joined forces there, we licensed that IP and then basically hardened that automotive-wise. What is that all used for? And where is Ethernet already in the market? Well, some of the car makers, I think BMW was the first who introduced a normal, a computer Ethernet switch into cars in 2007. That has nothing to do with the story that I just told you, but that had a totally different reason. In the manufacturing side, they could not manage to get the software into the cars fast enough. So if you try to put a DVD into a navigation system, and the navigation system then at the end of the assembly belt has via the CAN bus to distribute all that data, that takes you hours, yeah? So the cars could not leave the assembly belt quick enough. So what BMW did is they introduced several years ago an Ethernet port where they said, okay, here we are plugging the computers of the manufacturing side, doing the software downloading quick enough, download 2 gigabyte, and off we go. In the meantime, that is 100 million lines of code that a modern car has. So just to give you a figure, I think that's a jet fighter has in the range of 5 million lines of code, just to give you a bit of a difference there, order of magnitude. So high data rate download for software flashing in manufacturing is a huge issue. But for that, of course, you can take standard consumer electronics. You never have minus 40 degrees in a manufacturing site when you want to do software loading, nor have you 150 degrees. So it is a pretty straight setting. It is used once or twice every year maximum and under very stable conditions. So and you don't have an issue with the wiring harness because you have only a point-to-point connection to the main unit of the system. Yeah. So here the standard computer Ethernet broader reach or 100 base T is used consumer grade electronics. And now what is coming is what I had told you earlier. Suddenly you have all these systems, up to 15 cameras per car, up to 10 radar systems per car. And the issue that you see in there is each of those systems is providing loads of data, 10 to 20 megabit per second. And okay, you would say, great, Lars, fantastic, let's reduce that data, let's pre-process that data at the camera and then only send a few bits and pieces out. That does not work if you want to have advanced sensor fusion. So if you want to make sure that all data from around the car is reaching that brain, that gray box in the middle that I had shown you on one of the prior slides, then you need to make sure that most of that data directly goes to that big sensor fusion unit. Because that thing needs to have the best environmental information ever. Same is valid for the car-to-car communication. There's high data downstream. In the telematics, LTE advanced even goes theoretically up to 300 megabit per second. So there's loads of data going into that sensor fusion unit and are distributed around the car. So you have a lot of these point-to-fusion unit Ethernet connections in the network, and they are driven, of course, by systems like the adaptive cruise control as of today, radar systems, and the surrounding. On top of that, what we see now, of course, is more and more the car makers are changing the topology of the networks. Where it prior was a pretty much spaghetti code type of thing, You see now very well structured subdomains for these various branches, IP branches, and this is looking like a computer network more and more, simply because it's getting more complex, simply because you need to separate these domains from each other very clearly to make sure if someone hacks into one part of that network, the rest is not affected. You have firewalling in between. So all the issues of modern computer industry, you see now, of course, coming back here again. Plus, of course, you also want to have higher bandwidth for other systems. This is how a modern car network in the next 5 years will look like. So what I forecast from an Equus HKMC car, or from a 7 Series BMW, 5 Series BMW, Audi A8, Mercedes S-Class, and so on. You have one branch, head unit, infotainment part, rear seat entertainment, all connected via one control head unit, but in principle separated from the rest. And here you have the various Ethernet trees, yeah? Point-to-point connections, or even switches going down. Then again, this tree construction here to the body domain, to the main controller. One branch down, driver assistance systems, radar. This here, of course, would fan out into the various radar systems, the various camera systems, and so on. So you will get these type of tree structures in the car network, enabled, of course, via these physical layers that we have and the switches in between, where you can construct all of these sub-branches. Yeah? And then, of course, you have probably also these remaining flex-ray branches in the car for all sorts of actuators. So the X-by-wire applications where the 10 megabit are still sufficient. So what I meant prior is this type of architecture we are seeing in today's cars. This is how it's going to look like in future, and you have complete different know-hows in the car makers. Because what you see here is, it's for an IT specialist, this is the most boring picture ever. Unfortunately, or fortunately, the car making industry is of course led by managers that are very often coming from a very strong mechanical engineering domain. So where 20 years ago metal bending and welding were the innovations in the automotive industry, yeah? Then somehow these mechanics had been replaced by electronics in the car itself, and now suddenly the car opens up to the outer world. Yeah, but the skills of the managers, at least, the engineers maybe have followed, but the skills of the managers have not followed quickly enough. So there's a big change in the industry, and now these poor guys also have to deal with the issue that there is crazy young hackers out there that even try to screw these systems, and they are, let's say, furthest away from of course, their old home turf. So what we will see is, of course, the car makers are big time gearing up their IT expertise, hacking expertise, networking expertise. Yeah, and this is, of course, for us, it's fantastic. Yeah, security know-how in the company, networking know-how in the company, interfacing know-how in the company. Hooray! We hope that, and of course, microcontroller know-how in the company going forward. We hope, of course, to be the big leading partners for all these guys in future. So, just to conclude on that one, please.
Sorry, but are there any security standard for automotive Ethernet network?
Well, yes, and there are. There is security standards that are mainly driven by a microcontroller to microcontroller security, or that are even driven by specific secure elements. So what we are doing is we are bringing our banking card crypto controllers into those automotive control units. I can show you a telematics example. I have such a little module in my bag, where we have our banking card controllers. We are using these little encryption machines, Enigma machines, so to say, coding machines, next to the microcontroller and next to the physical layer, for making sure that you have a proper end-to-end encryption. So the Ethernet physical layer itself will have very little encryption, if at all, because like in email, if the two of us, we are sending us an email, it does not make sense that I send the email first in plain text to SS and SS forwards that email, because this plain text area could be attacked already. If I am the microcontroller and he is the physical layer, you are not secure in between. So what needs to happen is, your brain has the encryption of the code, my brain has the encryption of the secret code, and from brain to brain we can understand our messages. And then I communicate, and even if I tell SS the story in a totally weird dialect, and he is transporting that story, he cannot do anything with that story. You cannot do anything with that story, but the two of us, we can code and encode. So the security concepts in cars are very, very often microcontroller to microcontroller. Yeah, so basically, in a nutshell, of course, the key idea is we have the silicon out there in the market. We want now to develop that market, and what you see here at that demo here in front is, of course, this is a little bit of an Ethernet demo. Where you can say, how do we dream of a distributed car? Well, in future, in the past, you had everything in a radio unit, for example, all tuners, all things in the antenna. What you see here now is you have a radio module, you have a telematics, and you have a car-to-car module. This is the telematics module, this is the car-to-car module. All of that can go into a shark fin roof antenna. Here is the Ethernet switch, this little block, and here is 4 physical layers. Here the same. Here is our audio amplifiers, for example. And this is these twisted pair cables. So the infotainment head unit of the future just is an automotive qualified tablet PC. Purely digital engine, no analog anymore. All the rest is moving to the roof. And with that, for example, in a modern car, you can take out up to 20 euros of copper cable. At the moment, between the antenna and the head unit, you have more than 20 euros of coax cables, which is of course ridiculous. Yeah? And this is the play of NXP. What we want to do is we want to take the car makers and say, you know what? You give us 10 euro more for our chips, and we reduce your system cost by 25 euro. So everyone has a win-win, and this is what we're gonna make here as a system proposition. The same, of course, on the amplifier side. So if you have a digital amplifier next to the loudspeaker, we have intelligent amplifiers that have a feedback loop that can find out what quality of a loudspeaker they have sitting there next to the amplifier. If it is a degrading or if it is a crappy loudspeaker, the amplifier can start interacting. So the amplifier can pump up the volume, but if you pump up the volume too much, you would destroy the loudspeaker. So therefore, you clip the amplitudes, the destroying amplitudes, that you anyhow don't hear, because the loudspeaker is maxed out. You have this in mobile phones. You have a pretty crappy loudspeaker, a great amplifier with that feedback loop, and you get higher awards at the moment. We have really sound awards for our Maximus amplifiers. The same technology here. Just assume a leading edge car has 32 sound channels. Just imagine how much amplifier weight, how much energy consumption, and how much copper you are putting in such a premium car. It's totally ridiculous having this and then wanting to build lightweight cars. So if you can take small amplifiers, cheap speakers, and have these feedback loops, and having digital channels from the head unit or from the radio down there, digital routing via an unshielded twisted pair cable instead of such fat copper lines to the amplifier. Yeah, that's of course a perfect thing. Yeah, super weight saving, super distributed architecture will completely change this network as well, because suddenly you have a lot of the receiving thinking part in the roof antenna, only a bit of human-machine interface in the center stack, where the space anyhow is very, very precious, and the car makers would like to have more space available for the climate control and all of that stuff. And you have then basically all the rest distributed to the areas of the car where it is really needed. We've taken the same technology for the next innovation to make car-to-car communication more robust. Because what you have in car-to-car communication, maybe you all know these bent roofs of the Mercedes CLS. So really curved roofs, and at the very end the shark fin antenna is sitting. So with these type of constructions, of course, you never can look forward with your antenna, because you have a roof and a sunroof and all that shielding in between. You can perfectly look backward, but not forward. So you need a second antenna in the front. So we are taking at the moment our Ethernet physical layers, not the Ethernet protocol, but the same hardware, and we are connecting satellite antennas to the mother car-to-car antenna. So you have different antennas, and with that type of constructions, we can easily manage to have car-to-car communication systems working over 2 kilometers of range at 500 kilometers of speed. Why 500 kilometers of speed? Well, we have tested in Ingolstadt at Audi. This is one Audi A8 going maximum speed on a German motorway, 260 kilometers an hour. and another one. And if they approach each other, you are at a relative speed of 520 kilometers an hour. Yeah, so you have to be, in theory, of course, not happening every day, but in theory you can achieve speeds of that velocity. Yeah, and now that we have that technology in place, so car-to-car communication, we have also little car radar chips in place, but we are using these type of architectures to discuss with innovators on what can we do for drone-to-drone communication. You have flying drones, you want to have anti-collision systems that are very lightweight. As of today, you have anti-collision systems in airplanes that are 20 kilos. You have a drone of 3 kilo, you want to transport a parcel of 4 kilo, and you have a battery lifetime that is very limited. The last thing that you need is someone who tells you, you have to take an anti-collision system of 20 kilos with you. No, you want to have 20 grams. Yeah? And this is, of course, our system that we anyhow have in the automotive domain. Can we bring them to the right frequencies for avionics? If yes, okay, that might be a great use case as well for having drone-to-drone communication or anti-collision systems in drones available. And you see, so that's completely fanning out now into that whole robotics area, just because the cars are getting more automated and more robot-like. Okay, yeah, so that's basically the simple NXP automotive interfacing story. If you have further questions, of course, I'm happy to answer all of that. And other than that, of course, I'm also looking forward to separate interviews if you like to have us in there. Thank you.